Hello, everyone. Welcome to our Monday afternoon seminar. Today, it's a great pleasure to have with us Camile Bonvin from the University of Geneva, who will tell us about the anisotropic stress and the relativistic effects. Please, Camile, you have the floor.
Okay, so thank you very much for the invitation. It's really a pleasure to give this talk today. So today I want to talk about the large-scale structure of the universe, and more precisely about what we call relativistic effect in this large-scale structure, and how we can use this relativistic effect to test some property of the theory of gravity. And so here I will concentrate on what is called the anisotropic stress. So if we look at a map of galaxy like this one from the SDSS survey, where here each point represents a galaxy, we see immediately that these galaxies are not randomly distributed. They are grouped in clusters, in filaments, and so they draw a kind of pattern in the sky. And this pattern is what we call the large-scale structure of the universe. And it is actually very interesting in cosmology because this pattern is sensitive to different key ingredients in the description of our universe. So first, the large-scale structure is sensitive to the initial condition. So the fact that we see today inhomogeneities in the distribution of galaxies means that at the beginning of the universe, the matter and the radiation that we had were not homogeneously distributed. So there were some fluctuations, and we believe that these fluctuations were generated during inflation. So it means that the pattern that we see today in the distribution of galaxy is somehow related, somehow sensitive to the model of inflation that described the generation of perturbation. Then this distribution of galaxy is also sensitive to the theory of gravity, because the theory of gravity is what tells us how matter accretes around the initial seeds to give rise to larger and larger objects, so to the galaxies and the clusters. And so we expect that if we have different theories of gravity, if we have deviations from general relativity, we expect to see different patterns in the distribution of galaxies. And finally, the distribution of galaxies is also sensitive to the content of the universe. So obviously, it's sensitive to the amount of radiation and matter that we have. So they are the constituent of our galaxies. But this distribution of galaxies is also sensitive to the dark component in our universe. So to the dark matter that form the halos of dark matter in which the galaxies form, and also to the dark energy, because the dark energy has an influence on the expansion rate of the universe. And the expansion rate of the universe has obviously an influence on the way structure grow in this universe as a function of time. So again, we expect to see differences in the distribution of galaxy if our model is the simplest dark energy model, a cosmological constant, or if we have a dynamical dark energy. So from that, we understand that the large-scale structure really contains very valuable information about our universe. Now, of course, if we want to interpret properly this information, we need to understand exactly what we are measuring when we look at this distribution of galaxies. So what we usually do when we receive a map of galaxy is to pixelize it, so to split it in bins of solid angle and redshift, and then to count how many galaxies we have in each of these pixels. And actually, the quantity that we are interested in is the fluctuation in the number of galaxies from pixel to pixel. So we construct this observable delta, which is given by the number of galaxies in a pixel minus the mean number per pixel n bar and divided by n bar. So this delta is something that we can directly extract from a map of galaxies. It's an observable. And so the question is, how is this delta that we can observe related to the quantity we are interested in? So to the initial condition, the theory of gravity, and the model of dark energy. So in our first approximation, the answer to this question is actually quite simple. What we can say is that dark matter is not homogeneously distributed, so it will create gravitational potential wells. And then once the baryons have decoupled from the photons of the CMB, what they will do is simply feel the presence of this gravitational potential well, fall into them and form galaxies. So in this very simple picture, in the places where we see more galaxies, it means that we have more dark matter. And in the places where we see less galaxy, we have less dark matter. So our observable delta is directly related to the fluctuation in the distribution of the dark matter, which I call here delta O, divided by the background, the average amount of dark matter. And I call this ratio small delta here. Now, of course, we know that this picture is too simplified, and there are actually complications that modifies the relation between what we observe and the underlying distribution of the dark matter. So the first one is the presence of the bias. We know we have actually observed that the distribution of galaxy does not trace directly the distribution of dark matter, and that there is a bias here that relates these two quantities. And this bias depends on redshift and may also depend on scale at small separation. And then the second complication comes from the fact that we never observe directly the position of galaxies. What we observe is the redshift of the galaxy. So we look at the spectrum of a galaxy, we identify some line, and we see how these lines are shifted to the red by the expansion of the universe. So we measure that. And then we also measure the direction of the incoming photons. So if we would live in a universe which is completely homogeneous and isotropic without perturbation, from the measurement of the redshift and the direction of the photons, we could directly calculate where the galaxy is. Because in a homogeneous universe, if we know the redshift due to the expansion of the universe, we can calculate the distance between us and the galaxy. And also in a homogeneous universe, light propagates on straight lines. So if we know the incoming direction of the photon, we can directly conclude where the galaxy is. So we can reconstruct the Cartesian coordinates of the galaxies. Now, of course, we don't live in a universe which is perfectly homogeneous and isotropic. We have actually distribution, inhomogeneous distribution of the matter between the galaxy that we observe and us. And this will actually affect the trajectory of the photons. The trajectory will be distorted by all the structures that we have along the way. And this is very important because it will induce distortion in our coordinate system, in the coordinate system that we use in order to say where the galaxies are. And one very simple example is the Doppler effect. So suppose that I look here at a galaxy which is physically situated at the bottom of the potential. But then this galaxy, suppose that it is moving towards the observer, because there is, for example, another cluster of galaxy in front which attracts this galaxy. So this additional motion will actually slightly shift the spectrum of the galaxy here to the blue, because it's a motion towards the observer. And so if I use the redshift to infer the distance, neglecting the fact that there is this specular velocity, because I don't know what this specular velocity is, I will infer a distance which is slightly wrong. So I will conclude that my galaxy is situated here, slightly closer to me than it is in reality. So I make a mistake when I reconstruct the position of the galaxy. And we have similar effects transverse to the line of sight. So if there is a cluster between the galaxy and the observer, the light will be actually distorted, will be lensed by the presence of this cluster. And since the only part that I observe is the direction of the incoming photons, then if I conclude that the photons propagate on straight line, I will see the galaxy here, slightly shifted transversally with respect to its true position. So what this tells us is that when I look at a map of galaxy like this one, the structure that I see on this map do not reflect directly the underlying dark matter structure. The observed position of the galaxy are shifted transversally and radially, and therefore I see a distorted picture of the true distribution of galaxies. And so to extract information from a map of galaxy, we need, of course, to understand exactly what these distortions are, because if we don't understand that, if we don't model that properly, we will make a mistake when we analyze our data. So what I want to do in this talk is the following. So first, I want to show you what is the expression for this observable delta, encoding all distortions at linear order in perturbation theory. So I will always work here at linear order in perturbation theory, assuming that this departure from homogeneity are small. And so what we will see is that delta is given by fluctuation in the density, as we were already expecting, plus some distortion. And this distortion can be split into three terms. So there is the redshift-space distortion, gravitational lensing, and relativistic effect. And then what I want to show you is that this relativistic effect contains additional information compared to what has been measured until now. And so that we can use them to test for deviations from general relativity in a completely model-independent way. And I will describe in a bit more detail one of these tests, which is to test the relation between the two gravitational potentials that describe perturbation in the geometry of the universe. So let me start by showing you the derivation of this observable. So I will work in the following metrics. So I have a perturbed Riemann universe. I have a homogeneous background, which with a scale factor, which is given by this A here, which depends on time only. And then I have psi and phi that describe the perturbation in my geometry. And I assume that psi and phi are much smaller than 1. So if I have a metric like that, I can directly calculate the propagation of photons. So I have to calculate the null geodesic. And then from that, I can calculate what is the change in energy between the galaxy and the observer, and also what is the change in direction, what is the tangent to this geodesic and how it changes from the galaxy to the observer. And then from that, I can calculate the distortion in my coordinate system, which is the redshift and the direction of the incoming photons. And this will then allow me to calculate all the contribution to the observable delta. And this is what we find at linear order in perturbation theory. So the first term here was our naive guess, saying that the distribution of galaxy follows the distribution of the dark matter up to the presence of the bias. And all these other contributions come from distortion in the coordinate system that I am using in order to build these maps of galaxies. So if you look at this distortion, we can actually see that we have different contributions. So we have here contribution from the peculiar velocity of galaxies, which is the velocity that the galaxy have in addition to the Hubble flow due to structures in the universe. Then we have here in blue a contribution from gravitational lensing, which really describes the change in the trajectory of the photons due to the presence of structure along the way. And so this is an integrated effect from the source to the observer. And then we have here a lot of terms that depends on the gravitational potentials, on the metric potential phi and psi. And so some of these terms are local. They depend, like here, for example, on the value of the potential at the position of the galaxy we are looking at. And other terms like this one or this one, the Shapiro time delay or the integrated Sachs-Wolf, are integrating along the way. So they depend on the value of the metric, on the geometry, all the way from the source to the observer. So this expression really describes what we observe in the linear regime. It contains all the contribution to our observable in the linear regime. However, at the moment, it's not the quantity that is used to analyze current data. So to analyze current large-scale structure data, what people actually use is only the first two terms here. So the density fluctuation, and then this correction, which is called redshift-space distortion. I will describe it a bit in more detail in a moment. And they neglect current analysis, they neglect all the other terms. And actually they can do that because the other terms are strongly subdominant for the current survey. So for the scales and redshift that are probed at the moment by current survey. The other terms will become important for the coming generation of survey. So this lensing term, actually it has already been measured with quasars, so not with galaxies, but with quasars that are at very high redshift and therefore for which this term becomes important. And they will also be relevant for future surveys like Euclid or the square kilometer array. And then these last three lines encode what we call the relativistic effect. And for now, they have completely been neglected. So the question that we can ask ourselves is, are these relativistic effects relevant for future surveys? So first, will we be able to measure them? And if we can, is it interesting to measure them? So can we get new information about our universe by measuring these effects compared to the information that we already have from redshift-space distortion and lensing? So let me start by first trying to answer the second question. Do we get new information from this relativistic effect? So the current situation is the following. So with a large-scale structure survey, but actually also with the CMB, the quantity that we can measure is the density fluctuation, delta, and the peculiar velocity via redshift-space distortion. And then on top of that, we have also currently a measurement of the sum of the two metric potential, either by looking at the magnification of quasars, as I just showed you before, or by looking at cosmic shear measurement, so by looking at the change in the shape of galaxies that are correlated along the sky. So at the moment, we have actually 4 variables to describe the perturbations in our universe at late time. So we have delta, V, phi, and psi, but we have only 3 measurements of these 4 variables. So in general relativity, we actually know the relation between these different quantities. They are given by Einstein equation. So it's not a problem that we measure only 3 of them. But in general, if we want to test for deviations from general relativity, what we really want to do is to test the relation between these different quantities. And so obviously, this is not possible if we have just 3 measurements. We cannot test 4 different relations with 3 independent measurements only. So what people are doing currently when they test for the consistency of general relativity is to actually assume that some of the relations are known. So usually what they do is to assume that the continuity equation, which is an equation that relates the density perturbation to the velocity perturbation, and Euler equation, which relates the velocity to the time component of the metric. So people assume that these 2 equations are the same as in general relativity, that they are what they are. And then that deviations from general relativity are encoded in the other relation. And so they test this other relation. They test Poisson equation, and they test the relation between phi and psi. And so here in this context, you see that the relativistic effects are really a game changer, because what they do, this relativistic effect, is to provide an additional, a 4th measurement of one of this quantity, which is actually the gravitational potential, psi. So they provide a measurement of psi only instead of phi plus psi, which is measured with gravitational lensing. And so with relativistic effect, we will actually have 4 independent measurements. And with that, we can, of course, test the relation between the different quantities in a completely model-independent way. So we don't need to assume that the continuity equation or Euler equation is valid. We can really test directly these 4 relations. So if we go back to the expression for delta that I showed you, we see here what I was telling you about before. So here we have, in the relativistic term, this contribution, which depends on the radial derivative of psi, so the variation of psi in the direction of observation. And this is what we call the effect of gravitational redshift. And so gravitational redshift contribute to the relativistic effect, but not to the lensing and to redshift-space distortion. And that's why these relativistic effects are so interesting. Now, you could, of course, tell me, yes, the relativistic effects are indeed sensitive to psi, but they are actually sensitive to a lot of other terms. And so how can you claim that you can use that to measure psi? And so what I want to show you in the next part of this talk is that we can actually design the method to isolate this contribution from gravitational redshift from the other relativistic terms. So to really measure this variation of psi and then use that to test these different relations between the different variables. So what we need to do in order to isolate this contribution is to look at the correlation function. So once we have a measurement of the fluctuation in the number of galaxies in different pixels in a survey like this one, what we usually do in order to compress the information is to look at the two-point correlation function. So we look at the correlation of delta at two different positions, x and x prime, in our survey. And we actually average over all possible pairs of pixels that we have in the survey. And here, what is important is that the different contribution that I showed you in delta will actually affect this two-point correlation function in different ways. They will actually have different symmetry properties, and we can use these different symmetry properties or breaking of symmetry in order to target different terms and to measure different contributions separately. So to show you how these work, let me start by just showing you what happens if we consider only the dark matter density fluctuation contribution to delta. So our first naive guess saying that the distribution of galaxies follows the distribution of the dark matter. So if we look at the correlation function for a term like this one, we can easily show that the correlation function, which I call here psi, depends only on one parameter, d, which is the separation between the pixels that we correlate. And it's the only quantity that affects the correlation function. So the correlation function is completely isotropic. It does not care about the orientation of the pixel with respect to the observer. And this is really due to our initial condition. We believe, and actually most models of inflation predict that the initial fluctuation are statistically homogeneous and isotropic. And this is preserved by the evolution of the structures. Now, if we add the contribution from redshift-space distortion, so this term which depends on the gradient of the velocity, redshift-space distortion will actually break the isotropy of the correlation function. And we can understand that intuitively because what this term is doing is actually to change the redshift of the galaxy. We have this Doppler effect, Doppler shift. And therefore, if we look at galaxies that are in the same direction but at different redshift, this term can change the amplitude of the correlation function because it can change the apparent distance between these galaxies. It can change the redshift of each of the pixels, and therefore it can change the amplitude of the correlation function. So this term will contribute when we look at pairs of galaxies that are in the same direction. On the other hand, if we look at a pair of pixels that are at a fixed redshift, a fixed distance, but in two different directions, this term will actually vanish because in average, the velocity will be orthogonal to the direction of observation. So this term doesn't change the angular separation between the galaxies. And therefore, it has no impact on the amplitude of the correlation function for two pixels like that. So because of this redshift-space distortion, what we find is that the correlation function depends not only on the separation between the galaxy, but also on this angle beta, which describes the orientation of the pair of pixels with respect to the direction of observation. So it's possible to calculate the specific dependence in this angle beta. It has been done by Kaiser and Hamilton in the late 80s and beginning of the 90s. And what they found is that due to this redshift-space distortion, the correlation function has now the following form. So we still have one contribution, which is isotropic, but on top of that, we have a quadrupole and a hexadecapole. So we have a contribution that behaves like the Legendre polynomial of degree 2 of cos beta. And then we have another contribution that behaves like the Legendre polynomial of degree 4. And this is actually very interesting because it tells us now what we have to do in order to isolate the contribution from the velocity of the galaxy. So what we can do with our measurement is the following. So we can look at pairs of pixels, delta I, delta J. And if we sum over all pairs of pixels at fixed separation, what we will do is to measure the amplitude of the monopole. And we will get rid of these two additional contributions because when we average a Legendre polynomial of degree 2 or 4 over all directions, we obtain exactly 0. On the other hand, we can also measure the two-point correlation function, but weight each pair of pixels by the Legendre polynomial of degree 2. And if we do that, we get rid of the monopole and the hexadecapole, but we isolate the contribution from the quadrupole. And finally, if we weight by the Legendre polynomial of degree 4, what we do is to extract the amplitude of the hexadecapole. And so by combining that, by measuring separately monopole, quadrupole, and hexadecapole, we can then measure the density and the peculiar velocity contribution separately, simply because this density and velocity, they contribute in a different ways to the three different multiples. So if we measure the three of them, we can split the contribution of the density and the peculiar velocity. And this is something that has been done with a lot of success in surveys like BOSS, for example, or WiggleZ. So this is for the standard analysis, redshift-space distortion analysis. Now, what happens if we include relativistic effect? So the relativistic effect, they have an interesting property, which is that they break the symmetry of the correlation function. And by that, I mean that if I correlate a pixel with a different pixel, a pixel behind or a pixel in front, due to the relativistic effect, I will have an amplitude which is different. So of course, you see immediately that I can actually not measure such a breaking of symmetry if I have just one population of galaxies, because by construction, the correlation function has to be the same if I exchange a pixel front and back. But now if I split my population of galaxies into two populations, so a bright population, which contains all the galaxies brighter than some threshold that I fix, and a faint population, then I can actually look at the correlation between bright and faint. And what I'm claiming is that due to some of the relativistic effect, in particular this gravitational redshift contribution, the correlation function of a faint with a bright, a faint behind with a bright, will not be exactly the same as the correlation function of a bright with a faint galaxy in front. So how can we understand this breaking of symmetry? So for that, let me show you this very simple cartoon. So suppose that I have an observer here. He looks in this direction, and the observer sees three galaxies aligned in the same direction, one behind the other. So in front, he sees a faint galaxy, in the middle, a bright galaxy, and then behind, a faint galaxy. Now, let me assume that the bright galaxy sits at the bottom of a gravitational potential. This is actually what will happen in average in our surveys, because the brightest objects tend to be at the bottom, at the center of large clusters. So if I look at this bright galaxy, which is sitting at the bottom of a potential, then the light emitted by this galaxy has to climb from the bottom of the potential all the way up to reach the observer. And what general relativity tells me is that by doing that, the photons lose energy. So the spectrum of such a galaxy will be shifted to the red, in addition to the expansion of the universe, just due to the fact that the galaxy sits at the bottom of a gravitational potential. So if I use the redshift to infer the distance, then I will see this galaxy a bit further away than it is in reality. Then, if I look at the faint galaxy here, F2, which is in front of the bright galaxy, this faint galaxy is also in the gravitational potential, but a bit higher up. It's not exactly at the bottom of the potential, it's in the outskirts of my cluster. So the light emitted by this galaxy also has to climb out of the potential, but the climb is a bit smaller. So it means that this galaxy also appears a bit further away than it is in reality, but the shift is a bit smaller than the one experienced by the bright galaxy. And then if I look at the faint galaxy behind, I have chosen here on purpose a situation which is symmetrical. And so the faint galaxy behind will experience the same shift to the red as the faint galaxy in front. So now if I look at the separation between the galaxy, what we see is that the separation between the faint behind and the bright, D1, is now smaller than the separation between the bright and the faint in front. And since the correlation function depends on the separation between the galaxy, it actually decreases with the separation. what will happen is that the faint galaxy behind will be more strongly correlated with the bright than the faint in front. And so that's why we have a breaking of symmetry between a galaxy behind a bright one or in front of a bright one. So of course, this is just a cartoon. In reality, bright objects are not exactly at the center of clusters. The situation is more complicated. But if we do the calculation, this is actually the effect that will come out in average. So we can then use this breaking of symmetry in order to measure the effect of gravitational redshift, this effect due to the presence of a gravitational potential. So if I go back to the expression that I showed you here, so this is the effect that I described, this the effect of gravitational redshift. Now we can show that this is not the only quantity that will generate this breaking of symmetry between bright and faint. Actually, these two other contributions from Doppler term also generate an anisotropic correlation function. But this is actually not a problem because we have already a measurement of the velocity via redshift-space distortion. So we know that by combining the different things, we will be able to isolate this gravitational redshift step. So in order to understand how we can really isolate this term, we need to understand what is the form of our signal, what we should fit for in the data. So with my collaborators, we calculated the form of the correlation function, including this relativistic term, and we found that it has the following behavior. So it depends on the population of galaxies that we have, in particular on the bias of the two populations and the magnification bias, which is a quantity that we can measure from the population of galaxy. It depends, of course, on the separation between the galaxy. But then what is really interesting is that it depends on the orientation of the galaxy only via a cos beta. So we have here a dipolar modulation in the amplitude of the correlation function of the bright around the faint. And so this tells us immediately what we have to do if we want to target this term. What we need to do is just to look at the cross correlation of bright and faint weighted by a cos beta. By doing that, we will get rid of density and redshift space distortion, and we will directly target this relativistic effect that we are after. So at the moment, with current survey, it's not possible to measure this relativistic effect. The signal to noise is actually too small. We tried to measure it in BOSS, and we found that the signal to noise is below 1. But we also did some forecasts for the coming generation of surveys. So for DAISY, which has actually already started to take data. So DAISY will observe 10 million of galaxies at low redshift, where the dipole signal is the strongest. And the forecast showed us that we will be able to detect that we expect a signal to noise of this form. So this is the separation between the galaxy, and we can measure this dipole at different separation. And so you see that we expect a signal to noise well below 1 over a wide range of separation. And the cumulative signal to noise reaches 7.4. And in the further future, with the square kilometer array, which will start its second phase of operation in 2030, we expect a signal to noise of 46. So this means that in the future, we can really expect to measure these relativistic effects, and in particular, this dipolar modulation due to gravitational redshift. So,
sorry, Camille, can I ask a question? Can you go to the previous slide? So why do you have a peak in the signal to noise at roughly 20 megaparsecs?
So there is a combination. So the signal itself decreases with separation, but then in the noise, we have cosmic variance and shot noise. So at large scale, we are dominated by cosmic variance, at small separation by shot noise. And so in between, there is a sweet spot where actually both are subdominant. And so it's there that we have the most signal.
Yeah. And that 100 megaparsecs, I guess the bump is because of the BAO, right?
Yeah, exactly. You have a small bump due to the BAO.
Yeah. Thanks.
Okay, so then the question is, what can we learn from this dipole? Since we know that we will be able to measure it in the near future, which test can we do with this dipole? So since the dipole depends directly on the time component of the metric psi, we can use it to test directly the relation between phi and psi. So in a lambda CDM model where we have a cosmological constant, at late time, the two gravitational potentials are exactly the same. And actually, in many dark energy models, this relation holds also. So the two metric potentials are exactly the same. On the other hand, in most modified theories of gravity, the two metric potentials are different. So we have a non-zero anisotropic stress in modified theory of gravities. So it's very interesting to test the relation between these two quantities, because if we find that there is a non-zero anisotropic stress, this will rule out our simplest model and also many dark energy models. And if we find that there is no difference, a zero anisotropic stress, we can actually put very stringent constraints on modified theories of gravity. So this is actually a key test of deviations from general relativity. So how does this work in practice? So we need to combine the dipole with the other multiples if we want to isolate psi. So as I showed you, the dipole depends actually on various correlations. So we have the correlation of density with the time component of the metric, density with psi, which is the quantity that we want to measure, and density plus velocity correlated with the velocity. So if we want to isolate this contribution, we need to be able to remove the other terms. And for that, we use the other multiples. So the monopole depends on the density-density correlation, density-velocity, and velocity-velocity, the quadrupoles on delta V and VV, and the hexadecapole on VV. So it's actually very easy to combine these different multiples to remove this last contribution here in the dipole. And then the question is, what do we do with this delta V dot? So here it's a bit more complicated, but we showed with my PhD student here in Geneva, Daniel, that we can actually reconstruct this term in a model-independent way by looking at the evolution of the multiples with redshift. So with this future survey, DAISY and the square kilometer array, we will have measurement of the multiples in different redshift slices, actually quite thin redshift slices of width 0.1. And therefore, from that, by looking at the evolution of the multiple as a function of redshift, we are able to reconstruct this delta V dot. And so to remove it from the dipole without assuming any theory of gravity, which is really what we want to do. And so we were able to construct an observable, which is sensitive to exactly this quantity. So delta psi multiplied by the bias difference between the two populations of galaxies that we cross-correlate, so BB minus B. And then if we want to test for the anisotropic stress, we need another measurement. So we need a measurement of delta correlated with phi plus psi. And we can obtain that from gravitational lensing. So what we actually need to do is to correlate the shapes of galaxy at high redshift with the distribution of galaxy at low redshift. This is what is called galaxy-galaxy lensing. So the convergence kappa, we can obtain it either from the shear or from the cosmic magnification. And then we correlate that with delta. And we have an observable which is sensitive to delta times phi plus psi. So this galaxy-galaxy lensing is something that has already been measured with DES or with KITS, for example. The difference that the subtlety that we have to do here is actually to measure this galaxy-galaxy lensing, not for all population of foreground galaxies, but separately for the bright and for the faint. And so if we do that, then we will have an observable which is sensitive to the same bias difference times the correlation of delta phi plus psi. And then once we have that, we can actually just look at the ratio between this observable. And here everything will go away. So if we have no anisotropic stress, this ratio will be exactly equal to 2 at all redshift and at all separations. On the other hand, if we have a difference between the two metric potential, which here I encode in this parameter eta, then this ratio will be given by 1. plus eta. And depending on the model, this relation can vary with redshift and with separation. So this is a completely model-independent test. It relies on combination of the different observables, but there is no assumption about the theory of gravity. And we see immediately that if we find something which is different from 2 at any redshift or separation, we will have a non-zero anisotropic stress. So just to put things back into context, so what people are doing at the moment, because people say that they are actually able to measure the anisotropic stress, there have been measurement of the anisotropic stress with current survey. But what I want to show you is that these tests are not completely model independent. So what people usually do is to encode deviation from general relativity in these two functions, so eta that relates phi and psi, and mu that modifies Poisson equation. So it modifies the relationship between the density and the geometry of the universe. And then if we have a model like that, we can easily show that lensing measures this capital sigma, which is this simple combination of eta and mu. And what people claim is that redshift-space distortion measures directly mu. So it's directly sensitive to the modification to Poisson equation. And so here you can see that in this plot, in this measurement from a paper by Simpson and collaborator. So you see the constraint on mu and sigma. In red, you see the constraint from CFHST length, so measurement of lensing. And so you see that actually lensing is very sensitive to sigma, but insensitive to mu. And then redshift-space distortion in green, you see that it's sensitive to mu and insensitive to sigma. And so combining the two, we get a strong constraint on sigma and mu. And then, of course, we can translate that into constraint on eta. So this is the way the anisotropic stress is measured at the moment. So the relation between phi and psi. But actually, these measurements, they make one important assumption, which is that the continuity equation and Euler equation are valid. So what they do is to combine the continuity equation, the Euler equation, and the Poisson equation to get an evolution equation for the density, an evolution as a function here of the scale factor. And you see that this evolution depends on the background and also on this parameter mu, on this function mu. And then the velocity is related to the density simply via a variation, a derivation with respect to A. And so people claim that actually redshift-space distortion, since it measures delta and V in a model-independent way, provides a direct measurement of this mu, since the evolution of mu of delta is governed by mu. But this is actually correct only if the continuity and Euler equation are the same as in general relativity. If you have a modification in Euler equation, then you can rederive this evolution equation for delta, and you see that it depends on the modification of Euler equation, also continuity equation. And therefore, it's still true to say that redshift-space distortion measure directly delta and V, but then it's not true to translate this measurement into a measurement on mu. Actually, what you are sensitive to is a combination of mu and the parameter that enters into your modified Euler equation. And therefore, mu cannot be directly measured, and consequently, the anisotropic stress can also not be correctly measured. So if with this measurement here, one would detect a non-zero anisotropic stress, we wouldn't be able to say if it's really a non-zero anisotropic stress, or if actually the two metric potential are the same, but Euler equation is modified. The equivalence principle is not valid anymore. Whereas with our method, we don't rely at all on Euler equation or the continuity equation. So our method is completely model independent. We measure directly the relation between phi and psi. The drawback is that the dipole is more difficult to measure than the even multiples. And so obviously the constraint that we have on eta will be weaker. So at the moment we are working with my PhD student to determine how strong the constraint on eta will be for a survey like DAISY or the square kilometer. Okay, so to conclude, let me just briefly summarize the main message of my talk. So first, what I showed you is that the distribution of galaxies is affected by these relativistic distortions. And these effects have the particularity to break the symmetry of the correlation function, which is very important because it gives us a way of isolating these terms, of measuring them independently. So we have with that a direct measurement of psi, and then combining that with redshift-space distortion and lensing, we can build new tests of gravity. So here I describe one of these tests, which is the anisotropic stress. And actually with Pierre, we did another test, which is to test directly for the validity of the Euler equation. Okay, I'll stop here. Thank you.
Okay, thank you, Camille, very much for this nice talk. So we have ample time for comments and questions from the audience. Don't be shy, please ask. Yeah, Pierre.
Yeah, thanks, Camille, for the talk. I was wondering, towards the end, you were mentioning that so the current constraints on anisotropic stress are put by assuming both Euler equation and the continuity equation, and you said that if Euler's equation is violated, then there are consequences on those. But so you chose to insist on violations of Euler equation and not on the continuity equation. Is it because you believe that it's much less likely that there is a violation of the continuity equation? Is there any particular reason for this?
Yeah, that was my reason. That actually, I mean, in the end, the test that we do does not assume either. And the test that is done at the moment assume both of them. Mm. I think that it should be possible to do a test which assumes only one of them, only the validity of Euler equation. I think that then it should be possible to still measure the anisotropic stress. So I don't think it's necessary to assume both of them. This is what is done at the moment. Then the reason why here I just said Euler equation modified is actually because I have calculated what happens if you modify Euler equation. But if you modify the continuity equation, you would also get extra term.
Yeah, what would be the kind of physics that would lead to a violation of the continuity equation? Maybe decaying dark matter, things like this.
Yes.
Right.
Yeah. So if you have an exchange between, for example, dark matter and dark energy, then your energy is not conserved anymore. And so, yeah, you would change your continuity equation. So, then is it more likely than a breaking of the equivalence principle or not? I don't know. I think, but there are clearly models, but you know, we have worked on that together. There are models where you break naturally Euler equation just by coupling your dark matter to an extra degree of freedom that do not break the continuity equation.
I said that on the other hand, yes, I think I know someone in this group here who has worked on the other situation. I was wondering, Natalie, whether you wanted to comment on this.
No, well, yeah, all I would comment is that I think that in models where dark energy and dark matter are coupled, typically you still consider the total energy to be conserved, right? So I'm not sure you pick up extra terms there, but...
Yeah, so the total energy would be conserved, but the relation between the density of the dark matter and the velocity would be modified, I guess.
Yes.
Have an exchange of energy between the two. Yeah. And so there you would change the equation, meaning that you would also change the evolution equation.
Yeah.
Okay. Any more questions?
I can ask one if.
Yeah, please.
So when you're talking about the splitting of galaxies into two populations, is there a reason why you choose bright and faint? Could you choose anything else? Would it change what you're doing?
Yeah, it's a good question. So what really matters is the bias. So the signal is actually proportional to the bias difference between your two populations. So you could select by color, for example, as long as they have a bias difference, which is non-negligible, then you would pick up a a dipole. And so actually for this future survey, part of the game would be to try and understand what is the best selection of population to boost new signal signals. What is the best way to make this population very different in terms of bias?
Okay, thank you.
Okay. I also have a quick question, actually. So you mentioned that the main cause for the anisotropic stress is modified gravity, but there might also be some other cause like massive neutrinos. They also cause anisotropic stress. So with your method, how do you know that any deviation from what you expect in GR is due to modified gravity and not neutrinos, for example? How do you know?
You don't know. Actually, it's you measure just the anisotropic stress. But now the anisotropic stress created by the neutrino, the massive neutrino, is actually quite small. So there are these numerical simulations like G-evolution, where they try to include massive neutrinos. And I think, if I remember correctly, that actually the anisotropic stress is relatively small. But I mean, it depends on the how sensitive our constraint will be. But I think, but just by this method, there is no way to distinguish, to target the origin of the anisotropic stress.
Thanks. There is a question by Santi.
So thanks for the talk. I have a question about, so maybe you already explained this, but it's just to see if I got it correctly. So when you were explaining this potential and then the effective distance that we see of these the two different populations.
Mm-hmm.
So basically the idea is, so that the distance between the yellow and the blue galaxy will not be the same if we are, like, if one is behind and the other one is behind. And this will give us an effect on the dipole, on the cross correlation, right?
Yeah.
So, and what I didn't get then is whether this is the same effect, it will have an effect on the galaxy-galaxy lensing, or this is a completely different effect?
No, it's a different one. It's a different one. So the idea is really to measure this asymmetry here, which is sensitive to delta psi. And then for the lensing, there, what we measure is the correlation between the shape of galaxies behind an overdensity. So here what we probe is really the fact that the light emitted by this galaxy has to travel through the overdensity. And so it is lensed by this overdensity. So if we correlate the shape here with the distribution of galaxy here, we will see a correlation. And this correlation will be sensitive to the density of dark matter here and the phi plus psi actually integrated along the trajectory.
Okay.
It's another effect on top of that. Yeah.
Okay, it's another effect. So the other one wouldn't have any effect on magnification at all. It's just, I was wondering if it would be related, because it's, I guess because it's a kind of a line of sight effect. I was a bit confused between the two, but.
So it is there. Of course, you are right. In this delta, there is also the effect of gravitational redshift, which is slightly correlated with this one, but actually the correlation is very small. So it would be really a very subdominant effect that we can actually, that is neglected when people do the analysis, and it's a good approximation to neglect that, because it's so small that neglecting that in the modeling would just doesn't change the constraint.
Okay.
Whereas for the other one, we target this effect. It is also small in the other one, but we have a way of targeting it. It's not a small correction on top of something which is big. Here it's a small correction on top of something which is much bigger, so it's negligible.
Okay, well, thanks.
Yeah.
Okay, any more questions, comments? Okay, if not, then we can thank Camile again. Thank you, Camile, for this very nice talk again.
Thank you.
Thanks.
Pleasure.